Hello, in this video we're going to continue our tour of the somewhat mysterious diagram that Paul Erlich produced in around 2004, showing a number of musical temperaments. First I should say that if you haven't seen the first video in this series, this will make a lot more sense to you if you watch it first. Even if you're very familiar with this chart, please stay with me because I think we're going to be looking at it in a way you probably haven't seen before. Okay, let's start by looking at these bar charts up at top right. These show different tuning options for a given ratio, so they will change as we move around the chart. We've got 3 prime intervals corresponding to the second, third and fifth harmonics, and for each tuning the bars show how out of tune each prime is going to be. You've got a choice of tunings, remember, for each point on the chart, that's to say for each ratio. As you move around, you can literally see the primes fighting it out for who's going to take the biggest share of the damage. The longest bar means the biggest mistuning, the biggest deviation from just intonation. The top 3 bars show Paul Erlich's original tenny-optimal or top tuning, which tries to keep the damage to all prime intervals within the tightest possible limits. In the second row we've got I've called it L2, it's also known as TE or RMS. It's a more conventional notion of best fit tuning, and it's mathematically and computationally much more tractable than top, but to be honest I find that L2 and top usually seem to give rather similar tunings. Now the third set of bars is a bit different. It's what you get with so-called pure octave tuning, when no stretching or shrinking of the octave is permitted. The result, if you go to something which could do with some octave stretch or compression, you find that the other primes take the damage. Paul Erlich argued convincingly that if you want to optimize the tuning of all your intervals, not just the primes, you may need to stretch or shrink the octave. But it's now clear that other optimizations, such as L2, can be accommodated in the theory, provided they satisfy Paul's broader definition of top, which is tempered octaves please. Now if we take any of these temperament lines, the magenta lines, the tuning is going to change as we move along. Okay. Well, out here it's really nothing like just intonation. And out here at the other end, it's also nothing like just intonation. In the middle, if we follow a line, like for example the mean tone line, we're getting close to just intonation. And if we take the geometrically closest point on that line, and for this we'll need to zoom in quite a lot, and the just intonation point is right in the middle there. So the closest point on this mean tone line will be the L2 one, and I'll show them as green dots, the L2 tunings there. You can see this is pretty much sort of as close as it gets to the center. Now this is the green one. If you look, we've got some numbers, which are the actual sizes of the prime intervals for that L2 tuning. And if we move along a bit, somewhere very near here, there's the top tuning with some slightly different numbers. Now, if we take away the lines for a moment and Paul's original drawing, you can see, well I hope you can, that the green dots can be basically anywhere, but the blue dots, which are the top tunings, are on a few specific alignments. Now, if I put the contours back in, you can see that the blue dots congregate along these lines. If this was a relief map, these would be like kind of valleys leading down to this basin. So for most temperaments, and I could put some lines back in, if you literally look at something like this line, which is super Pyth, that's its nearest point, but it can dodge a little further down the hill and just inside that next contour to get a better top score, even though you might prefer the L2 tuning really. So one that's worth looking at is down here, Ripple. Again, its L2 tuning here has actually got an almost perfect octave. You can see there are a lot of zeros in that first number. If we try top tuning instead, here, we've slightly blown it with the octave now, and we've got a slight improvement to the third and fifth harmonics, but it's really nothing much. And this is why, certainly for an example like this, Ripple, many people might choose L2 rather than the top. Now, if we take something like Compton, temperaments like Compton and Blackwood run directly parallel to the contours, so there's a whole stretch. In this case, we can go in a bit. I'm going to just hide the L2s. And right, what you can see here is that there's this whole stretch which is running right along parallel to the contours. And now, if you watch the top bar chart, this is very tricksy because I can't actually follow this line. The brown and yellow bars stay pretty much the same, and it's only the blue ones changing. And the top damage is only measured on the worst mistuned intervals, which are the 2 and the 3 in this instance. So we're actually free in this case to adjust the blue bar to just intonation. So it should now be clear that we've got these two components of tuning. There's the ratio between the 3' intervals, which changes as we whiz around this chart. And then, without changing the ratio, we can stretch or compress all the intervals together, and that's what gives us these alternative tunings. The ratio controls all the structural properties of a tuning, things like its potential for building scales with 2 step sizes, or the options for generating the tuning from more convenient intervals smaller than the primes themselves. The stretch dimension affects the tuning's acoustic properties, the way overtones interact, and how the tuning will sound in different instrumental timbres. Paul's diagram shows the ratios, and to visualize stretch, we need to add the third dimension. These blue dots, they represent the top tunings of the various temperaments, and we've been seeing them so far as projections into the plane of the diagram. So now we're going to have a look at their true positions in 3-dimensional tuning space. So if we take the most prominent one in this view, you can see this is the top tuning of dicot, and that's quite stretched because it's above the plane of the diagram, and you can see that the first 2 primes, 1.006, 1.006, that's the factor by which they're stretched, and that includes an octave stretch of about 0.6%. So that's the real point where the top tuning exists. What you see on Paul's diagram is just its projection onto the plane. Now, okay, if I take the plane out there, now we can have a look and see each of, if we look at that dicot point, we can actually look down on it, and you'll see that that blue point is exactly in that plane along here, and that plane is dicot, and it's a plane now, not just a line, because the added dimension is the one where you stretch or compress the prime intervals. Some of the top tunings are not stretched, they're compressed, and we should be able to see those if we get the planes out of the way and look down underneath. So there you can see there are just as many protruding out the underside as there are above. And we could have a look and see what some of those are. I mean, that it seems is dimipent. That's Mavila. You can really quiz yourself with these if you want to. There is Nigripent. And they're all in there. You can see some of them are stretched and some of them are compressed. I mean, some of the stretched ones would include here Passion and Ripple, for example. Okay, so all this is going on in a very tiny region of tuning space. So now we've got the idea of this as a three-dimensional space. Let's actually zoom out in stages from this central region. Make sure the planes are there. And you can see rather more of those temperament planes, and the diagram still there. There's that triangle which delineates the musically interesting region with father, bug and dicot. So if we carry on, just as before, we find we're in a space where not much seems to be happening. And you know, you can see these are planes, but we're obviously extending this to tunings which are musically ridiculous, but mathematically interesting. So we'll carry on in, zooming out, zooming out. I mean, you actually practically lost sight of the area in the middle around just intonation where the diagram lives. And we can carry on out. And finally something happens. We catch sight of the outer walls of this sector of tuning space. And we've got this little kind of right-angled corner. And as before, the boundaries are where the prime intervals are tuned down to unison. Filling the space between these walls, there's this rather nice sheaf of temperament planes, all passing close to the just intonation point in the middle. None of them hits it exactly, but in this view you can't tell that. Everything looks perfect.